All right, let's dive into a classic computer science problem, one that you'll see pretty much everywhere, reversing a linked list. Now, I know it sounds a little intimidating, but we're going to break it down step by step visually, and I think you'll see that the logic behind it is actually way simpler than you might think. Let's get into it.
And right there, that's the absolute key. This is the big idea we're going to unpack today. Forget about the syntax, the for loops, the while loops for just a second. The real puzzle here, and the real solution, is all about how you manage the connections, the pointers, that link everything together. It's really more of a logic game than a coding test.
So that begs the question, right? What do we even mean by pointer control? Well, it's just the art of rewiring these links. It's about changing which node points to which, without accidentally breaking the whole chain or, losing a piece of your list somewhere in memory. And to do that, we need to know what tools we're working with.
So before we write a single line of code, let's meet the three main characters in this little drama. These are the pointers that are going to do all the heavy lifting for us. Here's our stage, a super simple three-node linked list. We've got 10 pointing to 20, 20 pointing to 30, and 30 pointing to null, which just means, hey, this is the end of the line. This is the exact list we are going to flip around.
First up, we've got cur, which is just short for current. Think of this as our spotlight. It's the node we are actively focused on and working with at any given moment. We're going to start things off with cur pointing right at the head of the list, that first node, 10.
Next up is prev for previous. Now this one is super important. It's always going to point to the beginning of our new reversed list as we build it. It's kind of like the anchor for our new chain. To start, since our reversed list doesn't exist yet, we'll just have prev point to null. And our third pointer is next. Just think of next as our safety net, or our insurance policy. Why? Because before we break a link and make our cur node point backwards, we absolutely have to save a reference to the next node in line. If we don't, the rest of the list is just gone, lost forever. So that is the one and only job of this next pointer.
Okay, so now that we've met our cast of pointers, let's see them in action. I like to call this the three-pointer dance, because it's this perfectly coordinated set of moves that we're just going to repeat over and over again for every single node in the list.
All right, here's the setup. This is where everyone starts. Prev is pointing to null, because our reversed list is totally empty. Cur is pointing at the head, node 10. And we'll use our next pointer to peek ahead and grab a hold of node 20. Everybody's in position. Let the dance begin.
The entire magic of this whole thing boils down to these 4 simple steps. That's it. For every node, we do these exact 4 things in this exact order. Let's walk through one full cycle, nice and slow.
Okay, step 1. We take our next pointer and have it grab onto node 20. This is so important. We have to do this first, because in the very next step, we're literally about to break the connection between 10 and 20. Without saving this link first, the rest of our list would just float away.
And here it is, step 2. This is the actual reversal. We take our cur node, which is 10, and we tell its next pointer to point to whatever prev is pointing at. Right now, that's null. And bam, just like that, the first link is reversed. Node 10 is now officially the new end of our reversed list.
Step 3 is just a bit of cleanup. Remember, prev's job is to mark the head of our reversed list. Well, we just added node 10 to that list, so we've got to update prev so it moves up and points to 10. Simple as that.
And finally, step 4. We've got to move our spotlight, our curve pointer, to the next node we need to work on. And how do we find it? Well, that's exactly why we saved it in our next pointer back in step 1. So we just set cur equal to whatever next was holding, and now we're focused on node 20. The first cycle is done, and we're perfectly set up to repeat those 4 steps all over again.
Okay, so we walked through the logic, we've seen the dance. Now let's see what this looks like as actual code. This is how that 4-step process translates directly into what we call an iterative solution.
See, this should look super familiar. We start our function, and the first thing we do is set up our pointers. We create prev and set it to null, and we set cur to the head of the list. This is a perfect match for the initial state we just visualized. And here's the heart of it all. The while loop is our dance floor. And inside you can see our 4-step dance, line for line. Step 1, save the next node in a temporary variable. Step 2, reverse the pointer. Step 3, move prev forward. And step 4, move cur forward. That's it. Once the loop is done, cur will be null
and prev will be sitting right on the new head of our reversed list, which is exactly what we need to return.
And hey, don't get too hung up on the C++ syntax here. The beautiful thing is, whether you're coding in C++ or Python or Java or whatever, the logic, that four-step dance, is exactly the same. The variable names might change a little, but the core algorithm is universal. Understanding the pointer movements is what really matters. All right, so that was the iterative approach. Now let's switch gears completely and look at a very different way to think about this problem: recursion. This one can bend your brain a little bit at first because it really requires a different kind of thinking.
This is the mantra you have to repeat to yourself when you're dealing with recursion. You have to take a leap of faith. Instead of going from start to finish, we're going to ask the function to call itself all the way down to the end of the list, and we just have to trust that the function will correctly reverse a smaller part of the problem for us.
Let's walk through this. That if statement is the base case. It just says if the list is empty or only has one node, well, it's already reversed, so just return it. The real magic is in the next few lines. Imagine we're at node 10. The line p equals reverse list head.next is that leap of faith. It's saying, hey, go reverse the rest of the list from 20 onwards and just give me back the new head of that reversed part, which would be 30. Now, assuming that works, p holds 30. Head is still 10, and head.next is still 20. Now look at this line. Head.next.next equals head. That's telling node 20, hey, your next pointer, point it back at me, at node 10. Then we set head.next to null, making 10 the new tail. And finally, we return p, which has been the new head the whole time.
Okay, so we've got two totally valid ways to solve this. Which one should you actually use? Well, especially in an interview, the answer almost always comes down to one critical factor: how they use memory.
And this right here is the whole story. The iterative solution is fantastic because it has O of 1 or constant space complexity. It doesn't matter if your list has 3 nodes or 3 million, we only ever create those same 3 pointers. The recursive solution, on the other hand, is O of n. Every time the function calls itself, it adds a new layer to the call stack. For a really long list, you could actually cause a stack overflow. And that's why, 9 times out of 10, the iterative solution is considered the better, more scalable answer.
So in the end, the secret wasn't about memorizing lines of code, was it? It was all about understanding that pointer dance. Once you can visualize how those connections are rewired, the problem becomes simple. You've untangled this classic data structure. The only question now is, what are you going to master next?